So imagine a society where um, everyone is working perfectly. Factories are booming, the labor force is fully employed, and while savings are just remarkably high.
Yeah, everyone is doing exactly what they're supposed to do in a capitalist system.
Right. And yet the underlying mathematics suggests that this society is practically guaranteed to either explode into catastrophic hyperinflation or, like, collapse into a devastating depression.
It's wild. Welcome to the terrifying reality of early macroeconomics.
It really defies common sense.
Yeah.
But when you look under the hood of long-run economic development, the engine is much more fragile than we like to admit.
That paradox is actually at the very core of our discipline. I mean, we naturally assume that an economy is like a pendulum, right? If it gets pushed a little bit out of whack, market forces will naturally swing it back to a stable center.
Yeah, that's what you're taught in Econ 101.
Exactly. But for a very long time, the most brilliant minds in economics were convinced that the economy was not a pendulum at all. They believed it was, well, a boulder balanced on the tip of a needle. Yeah. Any slight breeze, any minor deviation in investment or savings wouldn't just cause a wobble. It would cause a self-reinforcing, catastrophic crash.
Which brings us to our mission for today. Welcome to this custom-tailored deep dive. If you're tuning in, you are likely gearing up for a major intellectual challenge. You're mastering economic growth theory, specifically Part 1, for your IES General Economics GE-02 revision.
That's right. You're tackling Paper 2 at the elite master's programs, places like the Delhi School of Economics or JNU. And we know exactly what is on the line here.
Absolutely. Our objective today is to ensure you don't just, memorize a list of variables, but that you fundamentally absorb the structural logic behind them.
We're going to trace the entire evolutionary tree of growth theory. We'll start in the rather gloomy, pessimistic world of the classical economists.
The ones who mathematically proved that human progress was doomed to stagnate.
Right, those guys. And from there, we'll journey through the instability of the mid-20th century and finally arrive at the boundless optimism of modern endogenous growth models.
Yeah, and let's talk about the 2024 and 2025 IES question papers for a second, because the examiners are sending a very clear signal.
They definitely are.
When they ask about the instability of the Harrod-Domar model, or they ask you to compare the Solow model to endogenous growth, they aren't checking your ability to just regurgitate a textbook.
No, they're testing if you understand the underlying mechanics.
Exactly. Like, why does the system break down? Why do diminishing returns create a ceiling on human wealth? How do non-rival ideas shatter that ceiling? If you want those marks, you need the why.
A why is everything.
Okay, let's unpack this. Let's travel back to the late 18th century, the dawn of the Industrial Revolution, to look at the very first mechanical explanation for why economies grow.
That takes us straight to Adam Smith. Now, the popular imagination associates Smith almost exclusively with the invisible hand, right?
Yeah.
And the allocative efficiency of free markets.
Sure, the whole supply and demand thing.
Yeah, but if we're talking strictly about growth theory, Smith's engine of economic progress was something deeply physical. It was the division of labor.
Okay, lay that out for us.
To understand his model, you have to picture the world he was observing in the 1770s. Production was largely artisanal, like a single blacksmith or a single tailor would take raw materials and perform every single step of the process to create a finished good.
It's the classic image of the solitary craftsman in a workshop, which takes immense skill, but it's incredibly slow.
Precisely. Because it's slow, the output is really low. Smith famously observed a pin factory and noticed a radical shift.
The famous pin factory example.
Yes, if one unskilled worker tries to make a metal pin from scratch, drawing the wire, straightening it, cutting it, pointing it, flattening the head, they might manage to produce 1, maybe 2 pins in an entire day.
Which is terribly inefficient.
Right. But the factory owner didn't have one person doing everything. They divided the process into specialized, distinct tasks.
So one person only draws the wire.
Exactly. Another only cuts it. A third only sharpens the point. Suddenly, a small team of 10 people isn't producing 20 pins a day. They're producing tens of thousands.
That's incredible. By breaking the job down into hyper-specialized microtasks, the explosion in sheer productivity is just exponential.
It really is.
But how does that isolated factory trick translate into a macroeconomic theory of long-run growth? I mean, for a whole country.
The linkage is the creation of a surplus. Because those workers are producing thousands of pins, the capitalist factory owner sells them and makes a massive profit.
Makes sense.
And what happens to that profit is the crux of classical growth theory. The capitalist does not just, bury that gold in the backyard. They reinvest it.
Right.
They buy larger facilities, they purchase more raw wire, and crucially, they hire more workers. This reinvestment of surplus is the engine of capital accumulation.
Ah, so it's a feedback loop. The division of labor creates a massive leap in productivity. That productivity generates a profit surplus.
Yeah.
That surplus is reinvested as capital accumulation. And because the capitalists now have a larger factory and more workers, they can divide the labor even further, which creates even more productivity.
You've just described the virtuous cycle of Smithian growth. As long as markets are expanding to buy all these new pins, the division of labor drives profits, which drives accumulation, which drives further division.
It's a brilliant, optimistic, mechanical engine for increasing national wealth.
It was.
For time. Right, because this optimistic engine hits a massive physical roadblock just a few decades later. David Ricardo looks at this exact same industrializing economy, runs the math out a few generations, and concludes that the entire system is going to inevitably grind to a permanent halt.
Yeah, Ricardo injects a heavy dose of natural constraint into the economic models. To understand Ricardo's growth theory, you have to strip away the factories for a moment and look at the foundation of the 19th century economy.
Which was land and food.
Exactly. Ricardo argued that human economic growth is ultimately constrained by the physical limits of the earth, specifically the finite amount of arable land.
So walk us through the mechanics of this collapse, because on the surface, if a capitalist is making profits from textiles or iron, why does the amount of farmland dictate when their profits vanish?
It operates through the law of diminishing returns, combined with the rather grim view of human biology borrowed from Thomas Malthus.
Oh, the Malthusian trap.
Yes. Imagine a newly discovered, fertile country. At first, the population is small. They only bother to farm the absolute best, most productive land. The soil is so rich that a little bit of seed and labor yields a massive harvest. So food is cheap.
So far, so good. The capitalist pays the workers a low wage because food is cheap, and the capitalist pockets a huge profit to reinvest.
Right. But that reinvestment creates a demand for more labor. The capitalist needs more bodies in the factories. Here is where the Malthusian trap activates.
Okay.
The classical economists believed in the iron law of wages, which stated that the natural price of labor is merely the biological subsistence level.
Meaning just enough food and clothing to keep a worker alive and reproducing. So if the capitalist tries to pay them more because business is booming,
the workers temporarily experience a higher standard of living. But according to Malthus and Ricardo, they respond to this simply by having more children who survive infancy. The population surges.
right.
A generation later, the labor supply has expanded so massively that wages are pushed right back down to that biological subsistence floor. The real wage, in terms of purchasing power, is locked. It can never permanently rise above subsistence.
But now we have a much bigger population. We have all these new workers who were born during the boom, and they all need to eat.
That is the fatal turning point. To feed this larger population, society has to farm more land. But all the grade A, highly fertile land is already taken.
Ah, I see.
So farmers are forced to move up the rocky hillsides or cultivate marshy, inferior plots of land. Because this grade B land is worse, it takes significantly more labor and more capital to coax the same bushel of wheat out of the ground.
So this is the physical manifestation of diminishing marginal returns. You're putting in more effort for the exact same output.
Yeah, and this creates the famous Ricardian profit squeeze. Because wheat is now physically harder to produce on the margin, the price of wheat goes up across the entire economy.
Oh, man.
Now remember, the iron law of wages. The capitalist must pay the worker enough to buy their subsistence diet. If the price of wheat doubles, the capitalist has to double the nominal wage they pay the worker just so the worker doesn't starve to death on the factory floor.
Wait, let me make sure I have this straight. The capitalist is paying out vastly more money in wages, but the worker isn't actually experiencing a higher standard of living. They're still just buying the same loaf of bread.
Exactly.
Where is all that extra money going? Who captures it?
The landlords capture every single penny of it. Think about the person who owns that original highly fertile grade A land. They are still producing wheat cheaply, but they get to sell it at the new high market price determined by the worst land in cultivation.
Wow.
The gap between their low cost of production and the high market price is a massive surplus, and it goes directly into their pockets as rent.
So as the population grows, society moves to worse and worse land. The price of food skyrockets. The landlord's rents skyrocket. And the capitalist is forced to pay exorbitant nominal wages just to keep their workers alive.
Which leaves nothing left over for the capitalist. The residual profits shrink and shrink as the economy expands until eventually the profit rate hits exactly zero.
And think back to Adam Smith's engine. What drives capital accumulation? Profits.
Exactly. If profits fall to zero, the capitalist has zero incentive to invest. They stop building factories. They stop hiring. Net capital accumulation completely ceases.
The engine runs completely out of gas.
Utterly. The population stops growing because there is no new capital to employ them. The economy reaches a state of total, permanent stagnation.
The stationary state.
Yes. This is Ricardo's stationary state. It was a mathematical proof that humanity would eventually hit a brick wall of ecological limits, resulting in a society where a few wealthy landlords live in luxury, the masses live on the brink of starvation, and economic growth is dead forever.
It is an incredibly bleak thermodynamic view of human progress. You just run out of energy.
Pretty much.
But then Karl Marx enters the scene. He looks at this exact same trajectory. A booming capitalist system, inevitably marching toward crisis and zero profits, but he throws out the biological limits completely. Marx argues the system collapses, but not because of bad soil or too many babies.
Right, and that distinction is paramount for your IES revision. Ricardo's collapse is driven by natural constraints. Marx's collapse is driven by social and historical contradictions.
Okay, let's dig into that. Just a quick note for you listening. We're approaching Marx purely from an analytical standpoint here. We're looking at the mechanics of his economic model impartially, not endorsing the political ideology. We're just reporting the theory as it's tested.
Exactly. Marx operates on the framework of dialectical materialism. He looks at capitalism and says the problem isn't the physical earth. The problem is the inherent exploitative relations of production. For Marx, the engine of growth is capitalists extracting surplus value from the working class.
Let's define surplus value carefully, just the mechanics of it.
Sure. In Marx's economic model, a worker might produce enough value to cover their own subsistence in the first 4 hours of a shift, but the capitalist makes them work a 12-hour shift.
So there's 8 hours left over.
Right. Those extra 8 hours of value created by the worker are unpaid. That is the surplus value, and the capitalist pockets it as profit, which they then use to accumulate more capital.
Up to this point, it sounds a bit like Smith. The capitalist gets a surplus and reinvests it to grow their business. Where does the contradiction come in? Why does Marx think this destroys itself?
The contradiction is born out of market competition. Capitalists are constantly at war with one another for market share. To outcompete a rival, a capitalist needs to produce goods cheaper and faster.
Makes sense. How do they do that?
They bring in heavier machinery, they automate. In Marxist terminology, they increase the organic composition of capital.
That means they're spending a larger percentage of their total investment on physical machines, what Marx called constant capital, and a smaller relative percentage on living human labor variable capital.
Yes.
They're replacing workers with steam engines.
That is the trap. Marx theorized that physical machinery cannot create new surplus value. A machine merely transfers its own stored value into the final product over its lifespan.
Okay.
According to the labor theory of value, only living, breathing, sweating human labor can generate new surplus value.
I can see the mathematical paradox forming here. If my profit only comes from the surplus value of my human workers, but to stay competitive, I'm forced to fire my workers and replace them with massive, expensive machines.
Your base of exploitation is shrinking relative to your total investment. The total mass of capital in the economy is growing enormously because of all these new machines, but the pool of human labor from which profit is actually extracted is shrinking in proportion.
Oh, wow.
Therefore, the profit margin on that massive total investment has to inevitably go down.
So this is the Marxist falling rate of profit. It's not caused by the price of wheat going up on rocky soil. It's caused by the very technological progress that capitalism demands of itself. The system is structurally cannibalizing its own source of profit.
Beautifully put. And that falling rate of profit unleashes chaos. To try and maintain their absolute profits, capitalists squeeze the remaining workers even harder, depressing wages to the absolute floor.
Yikes.
They fire thousands, creating a massive reserve army of labor, a permanent underclass of unemployed who keep wages desperately low.
Yeah.
But this creates the ultimate fatal contradiction.
You may guess. If you replace everyone with machines and the few workers you do have are paid starvation wages, you have these incredibly efficient factories pumping out millions of cheap goods, but nobody has any money to buy them.
You trigger a crisis of overproduction. The warehouses are overflowing with manufactured goods, but the masses are destitute. Prices collapse. Factories go bankrupt and shut down.
It's a death spiral.
The crisis deepens until Theoretically, the working class simply cannot take it anymore, and the entire social structure shatters under the weight of class struggle.
Okay, so to recap the classical era, Ricardo said we had hit a physical wall of natural limits, and Marx said the whole system would collapse inward like a dying star due to technological unemployment and overproduction.
Right. Both predict the end of growth.
But clearly, neither happened. We didn't end up in a 19th century stationary state. We kept growing, so what did they miss?
They miss the true nature of technological disruption. The classical economists largely viewed technology as a slow, gradual accumulation of tools, or in Marx's case, a problematic substitution. They did not anticipate the violent, explosive, paradigm-shifting power of the entrepreneur. To understand how capitalism survived its predicted demise, we must turn to Joseph Schumpeter.
Joseph Schumpeter and the spark of creative destruction. This is where the narrative of growth gets highly dynamic. Schumpeter looks at the idea of an economy settling into a calm, static equilibrium, like Ricardo's stationary state, and basically laughs at it, right?
He dismisses it entirely. For Schumpeter, capitalism is fundamentally, inherently an evolutionary process. It is never stationary. It cannot be stationary.
Okay.
Growth is not just saving up money to build a slightly larger textile mill. Growth is a violent process of qualitative radical change. And the absolute center of this universe is the entrepreneur.
The IES exam often asks for precise definitions here, specifically distinguishing between invention and innovation. It sounds like semantics, but in Schumpeter's framework, they are entirely different concepts.
It is the most critical distinction in his theory. An invention is simply a scientific or technical discovery. Someone in a laboratory figures out the physics of a vacuum tube or the chemical formula for a synthetic dye.
So it's just knowledge at that point.
Purely a technical act.
Yeah.
It has no economic impact on its own. An invention can sit in a drawer for 50 years and generate zero economic growth.
So what transforms it?
An innovation. Innovation is the commercial economic application of that invention. It's when an entrepreneur takes that vacuum tube, figures out how to manufacture it cheaply, puts it into a consumer radio, builds a supply chain, and completely disrupts the home entertainment market.
So the scientist invents, but the entrepreneur innovates.
Exactly. Innovation is an economic act that creates massive market value.
The entrepreneur is the one who sees how to combine factors of production in completely novel ways. And this unleashes the core mechanism of Schumpeterian growth, creative destruction. Walk us through how this actually propels the economy forward.
Sure. Imagine a somewhat stable market, maybe the transportation sector in the late 19th century. It's dominated by horse-drawn carriages, blacksmiths, and feed stores. Everyone is making a modest, normal profit.
Sounds peaceful.
Then an entrepreneur arrives with a radical innovation. Henry Ford introduces the mass-produced automobile.
It's completely unprecedented. He has no real competition.
None. And because he is first, and is fulfilling a massive latent demand, he can charge a premium while producing cheaply. He earns astronomical monopoly profits, which Schumpeter called innovation rents.
I want to pause on that because normally in economics, we are taught that monopolies are inefficient and bad. But Schumpeter is saying that the prospect of achieving a temporary monopoly is the entire point.
Yes, it is the massive reward that justifies taking the insane risk of trying something new. That hits the nail on the head.
Okay, so it's a feature, not a bug.
Right. Without the lure of innovation rents, nobody would ever challenge the status quo. But these monopoly profits are strictly temporary. They act as a massive beacon to the rest of the economy.
I see.
Other capitalists see Ford making a fortune, and a swarm of imitators enters the market. General Motors, Chrysler, they reverse engineer the process. They build their own factories.
And as they swarm in, competition drives the prices down. The innovation rent gets competed away.
Yes. The new technology becomes the new normal. The market settles into a higher, vastly more productive state of equilibrium. The public has cars instead of horses, and society is wealthier.
But that's the creative part. Where does the destruction come in?
The destruction is what happens to the carriage makers. The blacksmiths, the buggy whip manufacturers, the stables. Their capital, their skills, their entire businesses are rendered completely obsolete practically overnight.
Ouch.
They are violently swept away. For Schumpeter, economic growth is not a peaceful accumulation. It is a brutal cycle where the new aggressively destroys the old, clearing the way for the next wave of progress.
It's a heroic, almost romantic view of capitalism, the brave visionary taking on the establishment and dragging society into the future.
It is.
But there is a deeply ironic twist in Schumpeter's later work. The source material highlights his paradox of decline. He actually agreed with Marx that capitalism would eventually end, but for the exact opposite reason. He said it would fail because it was too successful.
The irony is profound. Schumpeter argued that the very success of capitalist innovation destroys the sociological and institutional framework that supports it. He maps this out through what we now call the shift from Schumpeter Mark I to Schumpeter Mark II.
Unpack that transition for us.
In the early days, the Mark I era, innovation is driven by that heroic individual entrepreneur we just talked about, the lone genius in a garage, risking everything against the odds. It requires immense personal charisma, leadership, and a tolerance for chaos.
Okay, so that's Mark I.
But as capitalism matures, these successful ventures don't stay small. They grow into massive, dominant corporations. This is the Mark II era.
The lone genius gets replaced by an entire floor of an office building.
Precisely. Innovation undergoes a process of routinization. It stops being a risky individual leap of faith and becomes a predictable bureaucratic function. It is delegated to massive R&D departments.
So the romantic, risk-taking entrepreneur is replaced by teams of salaried technocrats, data analysts, and middle managers.
Yeah. The spark of creative destruction is basically corporatized into a spreadsheet.
Wow.
And that institutionalizes the economy into rigid oligopolies. These massive corporations erect huge barriers to entry to protect their market share, actively stifling any new disruptive creative destruction from below.
That makes sense.
But worse than that, it destroys the moral justification for capitalist wealth.
How so?
Well, if a single entrepreneur risks their life savings to build a railroad, society tolerates them becoming wildly rich. They earned it through risk. But when the company is run by nameless bureaucrats and the profits just flow to passive shareholders who took no active risk at all, the public loses its tolerance for immense wealth inequality.
Ah, the perception changes completely.
Right. Furthermore, this massive corporate wealth funds a growing class of intellectuals and academics who have the luxury to sit back and critique the system, promoting heavy regulations and socialistic bureaucracy that eventually suffocates whatever entrepreneurial spirit is left.
That is a dark turn.
If we connect this to the bigger picture, you can see this exact tension playing out in the modern economy. Look at the big tech monopolies today. They started as classic Schumpeterian Mark Burst entrepreneurs, college dropouts in garages disrupting massive industries.
Classic Mark I.
But today, they are quintessential Mark II bureaucracies. They hold immense market power, and they often just buy up small, innovative competitors to crush them, effectively freezing the cycle of creative destruction.
Contrast that with India's booming startup ecosystem, where thousands of state-recognized tech startups are currently fighting to be the next Mark I disruptors, desperately chasing those temporary innovation rents. It is a live demonstration of his theories.
Absolutely.
It is a phenomenal lens for analyzing modern market structures. However, for all of Schumpeter's sociological brilliance, he doesn't give us the precise mathematical tools to model macro-level savings and investment. The IES exam demands that we move from broad historical narratives into strict algebraic mechanics.
Yeah, we have to get into the math.
We need to dissect exactly how an economy balances its growth on a knife's edge. Let's step into the Harrod-Domar macro puzzle.
Right. We are now moving into the 1930s and 40s. Roy Harrod and Harrod-Domar, working independently, were heavily influenced by John Maynard Keynes.
Keynes had just revolutionized economics by explaining short-run depressions caused by a lack of aggregate demand.
Exactly. Harrod and Domar wanted to take Keynes's short-run static model and make it dynamic over the long run. They wanted to know the mathematical conditions required for an economy to grow steadily without falling into a depression.
And the entire architecture of their model rests on the alignment of three very specific rates of growth. If you're taking notes for the exam, this is where you need to lock in. Let's define these meticulously.
Okay.
First, the actual growth rate, denoted as G or GA.
The actual growth rate is empirical reality. It is simply the realized, recorded rate of growth in economic output over a given period. When the government announces that GDP grew by 6% last year, that is your GA. It is what actually happened.
Next is the natural growth rate, denoted as GN.
Think of the natural rate as the absolute physical speed limit of the economy. It is the maximum potential rate of growth on the supply side, and it is determined by exactly two external factors.
Which are?
The rate at which the labor force is growing demographically, plus the rate of exogenous technological progress. You cannot sustainably grow faster than the sum of your new workers and your new technology. That is the ceiling.
Got it. And finally, the cornerstone of the model, the warranted growth rate, denoted as GREW.
The warranted rate is a psychological equilibrium. It is the specific rate of growth that leaves all the entrepreneurs in the economy perfectly satisfied with their past investment decisions.
Why?
Because at this specific rate of growth, the amount of money households are planning to save exactly matches the amount of new physical capital that firms require to produce the goods people want to buy.
So planned savings exactly equals planned investment.
Yes. Because their expectations for demand are perfectly met, producers have no idle factories and no shortage of machines. Therefore, they are warranted or justified in continuing to invest at that exact same rate into the future. It's a state of perfect, steady confidence.
Now, this is a strict rule for our deep dive and a non-negotiable for your exam prep. You must visualize this relationship mathematically. I am going to dictate this equation fully. The actual growth rate equals the savings rate divided by the incremental capital output ratio.
Let's translate that into the standard notation the examiners expect.
Yes.
G equals small s divided by small v.
Okay, break that down.
Small s is the aggregate savings rate, the fraction of total national income that society chooses to save rather than consume. Small v is the incremental capital output ratio, or ICR.
Let's clarify ICR because it trips people up. What does it actually measure?
It measures the technological efficiency of capital. It tells you how many units of capital you need to produce one extra unit of output. If IV is 4, it means you need $4 of machines to produce $1 of goods. So the warranted growth rate, GRE, is fundamentally determined by society's planned savings rate divided by the technological requirement for capital.
So for an economy to experience a perfect golden era of stable, full employment growth, it requires an absolute macroeconomic miracle. The actual growth rate must exactly equal the warranted growth rate, and both of those must exactly equal the natural growth rate.
G equals GW equals GN.
And that mathematical requirement is the genesis of the infamous knife edge instability.
It really is. Harrod-Domar proved that this triple equilibrium is extraordinarily fragile. In most economic models, if a market is slightly out of balance, a price adjusts to fix it. If apples are too expensive, people buy fewer apples and the price comes back down. It's self-correcting.
Yeah.
The Harrod-Domar model is the exact opposite. Any tiny deviation from equilibrium is self-reinforcing.
It is often compared to balancing on a literal knife's edge, but I prefer a more industrial analogy to really explain the aggregate demand mechanism.
Let's hear it.
Imagine a massive concrete factory. The factory manager orders their raw materials based strictly on how much concrete they sold yesterday. If they are perfectly aligned with steady market demand, the system runs flawlessly. But what happens if they make a tiny mistake?
Let's map that to the macroeconomic variables. Suppose the actual growth rate, GAU, temporarily slips and exceeds the warranted growth rate, GAU. This means the economy is growing just a little bit faster than entrepreneurs expected.
So back at our factory, yesterday's sales were unexpectedly high. The manager's inventory is depleted. They realize they don't have enough capital machinery to meet this booming demand. So what is their rational response?
They panic and aggressively increase their investment orders. They try to build a new cement mixer or expand the warehouse. They need more capital instantly.
But, and here's the Keynesian trap, by ordering a new cement mixer, they are injecting massive new aggregate demand into the economy. The company that builds cement mixers now has a boom in sales, so they have to expand their factories, which hires more workers who buy more goods.
You see the feedback loop. The initial attempt to fix a small shortage of capital creates an avalanche of new demand, which pushes the actual growth rate even higher, blasting it further and further above the warranted rate. The economy spirals upward into an explosive, cumulative, hyperinflationary boom.
The manager ordered more materials, which artificially boosted the whole economy, making them think they need even more materials tomorrow.
Exactly.
And the reverse is equally terrifying. What if actual growth slips just a fraction below warranted growth?
The factory manager sees unsold concrete piling up in the yard. They realize they have excess, idle capacity. Their rational response is to cancel all future expansion plans. They stop buying machines.
Which instantly destroys aggregate demand for the machine manufacturers.
Which leads to layoffs. Workers lose income, so they stop buying consumer goods. The actual growth rate plummets even further below the warranted rate. You enter a death spiral of cumulative secular stagnation and massive, intractable unemployment.
Once you slip off the knife edge, gravity pulls you completely into the abyss.
That's the terrifying reality of the model.
This brings us squarely to the 15-mark essay question from the 2024 IES exam. The core question is, why is there no automatic mechanism to stop this? Why doesn't the free market just adjust interest rates or wages to naturally align the savings output ratio with the natural growth rate before the crash happens?
To answer that, you have to expose the rigid, immovable assumptions that Harrod and Domar baked into their equations. There are three massive rigidities in this model, and none of them respond to market prices.
Rigidity number one, the savings rate.
In this framework, the aggregate savings rate, small s, is purely behavioral. It is an ingrained habit of households. It does not dynamically adjust to the interest rate. Yeah. Even if the economy desperately needs more investment, you cannot easily convince a population to suddenly change their ingrained saving habits overnight. It's mathematically fixed.
Rigidity number two, the natural rate of growth.
The components of GN population growth and technological progress are treated as strictly exogenous. They happen outside the economic system.
Because they don't care about the economy.
Right. Population grows because of birth rates and medicine. Technology advances because scientists make discoveries. These things do not speed up or slow down just because the economy is in a recession. They are stubbornly independent.
And the final, most fatal rigidity, the capital output ratio.
Harrod and Domar assumed a Leontief-style production function. This means capital and labor must be used in exact, unchangeable, fixed proportions.
What does that look like in reality?
Think of a taxi cab. You need exactly one car and one driver to produce a ride. It is technologically fixed.
You can't substitute.
Exactly. Even if wages drop to zero because of massive unemployment, the taxi company cannot hire 10 drivers to drive one car. There is zero factor substitutability.
So the ratio is stuck.
Yes. Therefore, changes in wages or interest rates are completely powerless to alter the required capital output ratio.
So let's look at the terrifying picture this paints. You have three variables that dictate the fate of the economy: household saving habits, demographic birth rates, and inflexible engineering technology.
Right.
None of them talk to each other. None of them respond to prices. The mathematical probability of them spontaneously, perfectly aligning is effectively zero. And if they don't align, the entire system self-destructs.
It was a deeply unsettling conclusion for the economics profession. The direct policy implication was that capitalism is inherently, structurally unstable, and the only way to survive is for a massive state apparatus to constantly intervene.
Like with heavy fiscal and monetary policy to force the variables into alignment.
Yes. This logic heavily influenced the early five-year plans in post-independence India, where state planners obsessively tried to target specific national savings and investment ratios to manufacture stability.
But theoretically, academic economists couldn't just accept that the free market was a ticking time bomb. They knew the model was mathematically sound based on its assumptions, so the only way to save the concept of a stable capitalist economy was to attack the assumptions themselves.
They had to.
Someone had to find a way to make the variables flexible. So how did the profession rescue the knife edge?
The rescue came in two distinct ways, attacking different rigidities. The first brilliant fix came from Nicholas Kaldor at Cambridge, who decided to attack the assumption that the savings rate was a rigid constant.
Okay, so he's looking at small s.
Right. He argued that the aggregate savings rate of a nation is actually highly fluid because it depends entirely on how income is distributed between different classes of people.
He split the macroeconomic world into two groups, right? Workers who earn wages and capitalists who earn profits.
And he made one very realistic, observable assumption. Capitalists have a much higher marginal propensity to save than workers do.
That makes intuitive sense. If a factory worker gets an extra $100 in their paycheck, they're probably going to spend it immediately on groceries or rent.
Exactly.
But if a billionaire capitalist makes an extra $1 million, they don't eat $1 million worth of groceries. They save it. They buy index funds or invest in new businesses.
You got it. The capitalist savings rate is vastly higher than the worker savings rate.
Okay.
Now watch how Kaldor uses this to dynamically stabilize the knife edge.
I'm ready.
Let's return to the crisis scenario, where the natural growth rate, GIN, is greater than the warranted growth rate, GU. The economy has the labor capacity to grow faster, and investment demand is outstripping planned savings.
In the Harrod-Domar nightmare, this triggers the explosive inflationary boom.
Right. Kaldor agrees that inflation happens. But he says watch what that inflation does to the distribution of wealth. If demand outpaces capacity, the prices of goods shoot up. But historically, nominal wages are sticky.
Sticky, meaning they don't change fast.
Yes, they are locked in by union contracts or sluggish labor markets. Wages do not rise as fast as the price of goods.
So the price of the product the factory sells goes up 10%, but the worker's wage only goes up 2%.
which means the profit margin for the capitalist explodes. The profit share of the total national income increases dramatically relative to the wage share. Wealth is actively shifting away from the workers and into the pockets of the capitalists.
Oh, I see the mechanism. And because the wealth is now concentrated in the hands of the group that saves the most?
The aggregate overall savings rate of the entire macroeconomy automatically rises. And since the warranted growth rate equals is divided by V, as it naturally rises, GREW is pulled upward until it perfectly meets the natural rate.
Wow.
The system stabilizes itself entirely through shifts in income distribution.
It's an elegant, almost hydraulic fix. Caldor turns income inequality into a macroeconomic shock absorber.
It really is a clever solution.
But while the Cambridge School focused on savings across the Atlantic, Robert Solow was delivering the definitive neoclassical fix by attacking the other massive rigidity.
The fixed capital output ratio.
Right. The Solow growth model is arguably the most famous and influential model in the history of macroeconomics.
Solow looked at Harrod's assumption that you absolutely cannot substitute capital for labor and said, that might be true for a taxi cab in the short run, but across an entire economy over decades, it is absurd.
Because if a resource becomes expensive, humans are incredibly ingenious at finding a way to use less of it.
Precisely. If labor becomes scarce and wages rise, firms will not just sit there and go bankrupt. They will adapt their engineering, they will invest in automation, and buy more machines to replace the expensive labor.
And vice versa.
Yes. Conversely, if capital is scarce and interest rates are sky high, they will adopt labor-intensive production methods.
To model this, Solow introduces a well-behaved neoclassical production function. The most famous example is the Cobb-Douglas function.
Right, which allows for smooth, continuous substitution between capital and labor.
And what's the result of that?
Because you can substitute factors based on their price, the capital output ratio, V, is no longer a fixed technological parameter. It is entirely flexible.
Which solves the problem.
And this single change completely dissolves the knife edge. If the economy veers out of balance, changes in relative prices, wages adjusting against interest rates, will incentivize firms to change their mix of capital and labor, smoothly and automatically guiding the economy back to a stable, long-run growth path.
So, to truly grasp the Solow model for the IES exams, we have to move beyond the narrative and look at the core engine of his theory.
We definitely need to look at the math of capital accumulation.
If you want to prove to an examiner that you actually understand Solow, it all comes down to visualizing this one specific equation.
And I will dictate the fundamental differential equation of the Solow model, word for word. In the Solow model, the change in capital per worker over time equals investment per worker minus the depreciation rate times capital per worker minus the population growth rate times capital per worker. At steady state, this entire expression equals 0, which pins down the steady-state capital stock.
Let's translate that math into a visual reality for everyone listening. Think of the economy's capital per worker as a massive bathtub of water. You want the water level to rise because that means each worker has more machinery, making them more productive.
Okay, I like this analogy.
There's a faucet pouring water in, and there's a massive drain pulling water out. It's a battle between two forces.
The faucet pouring water in is actual investment per worker.
Mm-hmm.
Society saves a portion of its income and builds new machines. This force attempts to push the capital per worker up.
But the drain is constantly trying to pull the water level down. And in Solow's model, that drain has two components. First, physical depreciation.
Right. Machines rust. Tractors break down. Computers become obsolete. A certain percentage of your capital stock just vaporizes every year due to wear and tear. You have to invest money just to replace what broke.
And the second part of the drain is population growth.
New workers are constantly being born and entering the labor force. If you want the average amount of capital per worker to stay exactly the same, you have to build enough brand new machines to equip all those new arrivals.
This gives us the crucial distinction between capital widening and capital deepening.
Yes, capital widening is running on a treadmill just to stay in place. It is the exact amount of investment required to replace the rusted machines and equip the new workers, ensuring the capital per worker ratio doesn't fall.
But if your society saves enough money that your actual investment is greater than the widening requirement, you achieve capital deepening.
The faucet is pouring water faster than the drain can pull it out.
Exactly. The water level rises. Capital per worker increases. Every worker now has more tools, so output per worker rises, and the economy experiences true per capita growth.
But here is the genius and the ultimate tragedy. of the Solow model. This capital deepening process cannot go on forever
Why not?
because it is tethered to the iron law of diminishing marginal returns.
Let's explain why. If I am an accountant with no computer, I am very slow. If you invest capital and buy me my first laptop, my productivity skyrockets. That first unit of capital is incredibly powerful.
But what happens if society keeps saving, keeps investing, and buys you a second laptop?
I mean, maybe I can look at 2 spreadsheets at once. It helps a little.
And a third laptop, a fourth. Eventually, you run out of hands.
True.
Each additional unit of capital adds less and less to your total output. The marginal product of capital strictly declines.
Let's bring this back to the bathtub equation. Because of diminishing returns, the extra output you get from new machines starts flattening out, which means the extra savings you generate to buy more machines also flattens out. The faucet is losing pressure.
Meanwhile, the drain is relentless. Depreciation and population growth increase at a constant linear rate.
That sounds like a problem.
It is. If you have 10 million laptops, you have a massive amount of depreciation to cover every single year. Eventually, the sheer, crushing cost of replacing broken machines and equipping new workers will entirely swallow up every single penny of your investment savings.
So the faucet and the drain exactly equalize.
And when they equalize, the change in capital per worker drops to exactly 0.
Welcome to the steady state.
There it is.
The water level stops rising. Capital per worker is frozen. Because you aren't giving workers any more tools, output per worker is frozen. Per capita economic growth comes to a dead, permanent halt.
The aggregate size of the economy is only growing at the exact rate of population growth, but individual wealth is permanently capped.
Before we look at how this plays out in the real world, we need to address a specific normative concept that is heavily tested alongside the steady state. The golden rule of capital accumulation, developed by Edmund Phelps.
The golden rule asks a very human question. An economy can end up in many different steady states depending on its savings rate. A country that saves 10% of its income will have a different steady state than a country that saves 50%. Which one is the absolute best for society?
And in economics, best doesn't mean having the most factories. It means maximizing human consumption. We build economies so people can eat well, live in nice houses, and enjoy their lives. You cannot eat a tractor.
Exactly. If a society decides to save 100% of its income, it will accumulate a massive mountain of capital. But the citizens will literally starve to death because they aren't consuming anything.
That's a bad steady state.
Very bad. The golden rule identifies the Goldilocks zone. It is the specific steady state where the gap between total output and the required investment is at its absolute widest, leaving the maximum possible amount of resources left over for human consumption.
The mathematical condition for this is frequently tested. It occurs where the marginal product of capital exactly equals the population growth rate plus the depreciation rate.
Yes, in the standard notation where the slope of the production function A prime of K star equals n plus delta.
It is the pinnacle of neoclassical efficiency. But we have to step back and look at the macro implication of Solow's proof. Solow mathematically demonstrated that because of diminishing returns, just saving money and piling up more physical capital cannot sustain long-run growth.
You inevitably hit the steady state wall.
The model suggests we just end up in a slightly richer version of Ricardo's gloomy stationary state. But historically, that hasn't happened. The United States, Western Europe, they have been growing for centuries. They didn't hit a wall.
No, they didn't.
So how does the Solow model explain real-world data?
It's fascinating to look at historical case studies through the lens of Solow. Consider the economic miracles of West Germany and Japan immediately after World War II.
Okay.
Their physical capital, stock factories, bridges, railways, was completely destroyed by the war. Their bathtub was empty.
But because they had almost no capital, the marginal product of whatever new capital they built was astronomically high, that first new laptop principle.
Yes. Because they were so far below their steady state, the Solow model predicts they should grow incredibly fast as they accumulate capital to catch back up.
And that is exactly what happened. They experienced double-digit growth rates for a decade. This is known as conditional convergence.
But contrast that with the Soviet Union during the Cold War.
Ah, right.
The Soviets forcefully extracted massive savings for their population and engaged in the most aggressive capital accumulation program in human history. They built giant steel mills and tractor factories everywhere.
And initially, they grew rapidly. But by the 1970s and 80s, Soviet growth ground to a halt. Why? Because they hit the Solow steady-state wall.
Precisely. They had accumulated massive amounts of capital that they ran headfirst into diminishing returns. They filled the bathtub, but they couldn't grow any further because they lacked the one crucial variable that Solow said was necessary to escape the steady state.
Exogenous technological progress.
Exactly. Solow realized his model doomed economies to stagnation unless the actual production function itself shifted upward over time.
So technology changes the rules.
He argued that technology improves, making labor and capital fundamentally more productive. This allows an economy to break through the steady-state ceiling.
When economists look at historical data, they measure this technological progress as the Solow residual, or total factor productivity, TFP.
It is called a residual because it is literally what is left over.
Like the math that doesn't fit.
Basically, if you measure how much an economy grew, and you subtract the growth that can be explained by adding more labor, and you subtract the growth explained by adding more capital machines, the mathematical remainder is the Solow residual.
It's the growth we can't explain with physical inputs. It's often called a measure of our ignorance.
Solow essentially says, the economy grows permanently because of technology, but my model cannot explain where technology comes from. It just falls from the sky exogenously like manna from heaven.
And while that made the math work, for theoretical economists, answering the fundamental question of human progress by shrugging and saying magic technology from the sky was deeply, intensely unsatisfying.
Extremely unsatisfying.
Which brings us to the final evolution and the focus of the 2025 IES paper, endogenous growth theory.
Right. In the 1980s, a new generation of economists, led by figures like Paul Romer and Robert Lucas, decided it was time to crack open that black box of technology.
They wanted to build a model where sustained, long-run growth was generated endogenously.
Meaning it is driven by the deliberate internal actions of people and firms, not by unexplained exogenous shocks.
Their monumental task was to figure out a way to break the curse of diminishing returns mathematically. Solow proved that as you accumulate more capital, it becomes less productive. How do you bypass that iron law?
You do it by fundamentally redefining what the word capital actually means. Lucas focused heavily on human capital, the idea that investing in education, skills, and on-the-job training makes workers permanently more productive.
And Romer.
Paul Romer's Nobel Prize-winning breakthrough was focusing on the specific economics of ideas and knowledge. He introduced a concept that is absolutely paramount for your exams, the non-rivalry of ideas.
Let's unpack non-rivalry, because it completely changes the physics of economics.
Traditional physical capital is rival. If I am driving a specific tractor on my farm, you cannot drive that exact same tractor on your farm at the exact same time. We are rivals for its use. It is a scarce physical object.
Right.
But an idea is fundamentally different. An idea is non-rival. Think of the chemical formula for a new life-saving pharmaceutical drug, or the engineering blueprint for a more efficient microchip, or even just a clever new way to organize an assembly line.
Once that idea is generated, its use is infinitely scalable. If I use the mathematical formula for a drug, it does not deplete the formula. It doesn't stop you from using the exact same formula at the exact same time.
And this unique property of non-rivalry creates massive economic phenomena known as knowledge spillovers.
Knowledge spillovers?
When a firm spends millions of dollars on R&D to invent a new technology, they might patent the specific physical product. But the underlying foundational knowledge inevitably leaks out into the broader economy.
This is why tech clusters like Silicon Valley or pharmaceutical hubs exist. The knowledge is literally spilling over between companies, engineers talking at coffee shops, employees moving between startups.
Yes. Other engineers learn from the breakthrough, they build upon it, and they become vastly more productive themselves without having to pay for the initial R&D.
Which is huge.
Because of these massive positive externalities, when you invest in knowledge, you aren't just making your own factory more productive. You are inadvertently making the entire macro economy more productive.
And this is the magic key that defeats Solow. These knowledge spillovers are so powerful that as you accumulate more knowledge capital, the spillovers offset the diminishing returns of the physical machines.
This leads us to the simplest, most elegant mathematical expression of endogenous growth, which serves as the foundational stepping stone for the complex models.
The AK model.
The AK model. If there is one equation that defines the shift from neoclassical to endogenous theory, this is it. Let's introduce the production function.
Okay, hit us with it.
The AK model strips away all the mathematical complexity of Cobb-Douglas to make one devastatingly important point. The production function is simplified to just y equals AK. Total output Y equals a constant number A multiplied by K.
But the K here is fundamentally different from Solow's K.
Yes, K in this model is broad capital. It includes the physical machines, yes, but it aggregates human capital and the entire accumulated stock of non-rival knowledge into that single variable.
Oh, that makes sense.
Because this broad K includes knowledge, which generates those massive spillovers we just discussed. As you accumulate more and more of it, you do not experience diminishing marginal returns.
The marginal product of capital, which is represented by that constant letter A, never falls. It stays perfectly constant no matter how incredibly massive your capital stock becomes.
Exactly.
The 100 millionth laptop is just as productive as the first laptop because it is loaded with infinitely scalable, better software.
Now, we must dictate the final growth equation for the exam. Because A is constant, it fundamentally changes the long-run trajectory. I will dictate the growth equation fully. The steady-state growth rate equals the savings rate times the marginal product of capital minus the depreciation rate.
So in mathematical notation, long-run growth, G equals small s multiplied by capital A minus delta.
Look closely at the implications of that equation. In Solow's world, as capital grew, the marginal product fell, pushing the growth rate inevitably to zero.
Right.
But in the AK model, S is a constant. A is a permanent constant, and depreciation is constant. Therefore, the growth rate, G itself, is a permanent positive number.
Which means there is no zero growth steady state. The bathtub never stops filling. The economy just keeps growing forever, driven entirely by its own internal savings and its deliberate investment in knowledge and R&D.
What's fascinating here is that we have finally mathematically solved the classical curse.
Look at the intellectual journey we've just taken.
It's been a long road. We started with Ricardo's gloomy prediction that finite land would starve us all. We moved through Marx's assertion that technological substitution would destroy profit rates and trigger collapse.
Then we navigated Harrod-Domar's terrifying instability where one wrong move caused a depression.
We hit Solow's frustrating conclusion that even if we are stable, capital accumulation alone eventually runs out of steam.
And endogenous growth theory arrives and provides a rigorous mathematical proof that humanity is not doomed to stagnate.
It's incredible.
As long as society continues to save, and crucially directs those savings toward human capital, scientific research, and the generation of non-rival ideas, our capacity for economic growth is theoretically boundless.
It is an incredibly optimistic, empowering conclusion to a discipline that was once dubbed the dismal science.
It really is a remarkable intellectual progression. Every single model we discussed today was essentially built to solve the fatal underlying flaw of the model that came immediately before it.
That's the nature of academic progress.
Now, let's bring this all together and deliver the actionable value for your IES 2026 exam prep. Based on the patterns established in 2024 and 2025, here are the 3 most likely ways examiners will test your command of growth theory part 1 next year.
First, expect a rigorous mathematical derivation. You must be prepared to derive the Solow steady-state equilibrium from scratch, defining capital deepening and widening, and subsequently using calculus to prove the golden rule of capital accumulation, where consumption is maximized.
You really have to know those differential equations cold.
Second, the qualitative essay. Be prepared to write a detailed explanation of exactly why the Harrod-Domar model lacks an automatic stabilizing mechanism. Do not just say it's unstable.
Well, be specific.
You must explicitly detail the 3 rigidities, the behavioral savings rate, the demographic exogenous population growth, and critically, the Leontief fixed capital output ratio that prevents price substitution. That is where the heavy marks are awarded.
And third, a comparative macroeconomic analysis. You will likely be asked to contrast the convergence hypothesis of the Solow model, the idea that economies inevitably slow down and hit a steady state driven by diminishing returns, against endogenous growth model's promise of sustained, limitless long-run growth, driven by the non-rivalry of knowledge and spillovers.
Master those 3 conceptual pillars, and you will have absolute bulletproof command over this section of the syllabus.
But before we let you go back to your notes and past papers, I want to leave you with a final provocative thought that weaves these historical theories into the reality of tomorrow.
Oh, this is good. We ended our historical journey on the soaring optimism of Paul Romer, the belief that non-rival ideas drive endless compounding human growth.
But cast your mind back to the middle of our discussion. Remember Joseph Schumpeter's dark warning, the paradox of decline?
Right.
He warned that the chaotic, brilliant spark of innovation eventually becomes captured and suffocated by sterile, monopolistic corporate bureaucracies.
It is the ultimate tension in modern economics. The boundless potential of human ideas versus the institutional decay of the massive corporations that ultimately control them.
So apply that tension to the rise of artificial intelligence today. AI is arguably the ultimate non-rival idea in human history, an engine capable of generating unimaginable knowledge spillovers.
Absolutely.
Does AI permanently elevate our A in the AK model, effectively guaranteeing limitless accelerated future growth for all of humanity? Or when you look at the billions of dollars of massive capital required just to train these models, is AI merely another wave of creative destruction that has already been captured, locked down, and bureaucratized by monopolistic big tech companies?
Are we heading right back to Schumpeter's stagnant Mark II era?
Exactly. Will AI liberate our economic growth, or will it just build a taller wall around it?
That is the multi-trillion-dollar macroeconomic question of our era, and the exact kind of high-level synthesis you should be striving for.
It is something for you to mull over as you hit the textbooks tonight. Keep questioning the assumptions behind the models. Keep looking for the why hidden in the math. And best of luck on your IES revision.